So, hi everyone. So today is the last presentation in the P4 Expert Roundtable series, and I'm very excited to welcome you all to this final presentation. My name is Mohammed Shahbaz, and I'm a postdoc at Stanford University and the moderator for this talk. It is my pleasure to have J.K. Lee in today's roundtable session. He is going to talk to us about his work on advanced congestion and flow control using programmable switches. So I will now hand over to J.K. to introduce himself and talk about this amazing work. So over to you, J.K.
Okay, hi everyone. I'm J.K. Lee from Intel Barefoot division. It's my honor to talk about some of the new programmable building blocks that we made available in Tofino 2 and their P4 representations and some of the use cases. So yeah, first I'm going to introduce the 3 new building blocks that are becoming available in the Tofino 2 programmable data plane. And they can be very well used for the various congestion and flow controls. And quickly just going through the list, we can provide something like a egress side queue congestion information at Ingress Pipeline. And we do have also more flexible and programmable packet generation logic and advanced flow control in the data plane. And these features can be used for many different very interesting use cases. We are going to talk mostly about source quenching as one representative use case to demonstrate the features. And a little bit discuss a little bit about the interaction between the source quenching or pause with the existing end-to-end congestion control schemes. This is a really exciting moment for us because some of these building blocks that we have built for years in the hardware and also the relevant software supporting logics and also application on top. It's a lot of work from the a group of talents and from Intel and Barefoot, and also Robert Suley in Yale University and Aditya Akila and his students and the University of Wisconsin Madison on helping us and working with us on this, creating the existing use case of source quenching. Okay, so the very first step for us to make any reaction to congestion is to know about the congestion. And as you may be familiar with the PISA and Tofino architecture, on the right-hand side, I have a very simplified version of this PISA pipeline. We have a programmable parser and set of Ingress MAU pipeline, deparser, and here where we actually make all the routing and then queuing decisions. An actual queuing system is sitting in between the ingress and egress pipeline. Once packet is dequeued out of this queuing system and going into the egress pipeline, where mostly this queuing information become available as a egress intrinsic metadata. There are some other architectures that I know that queuing information, for example, depth of the queue or congestion information is available pre-queuing, but mostly they are becoming available after the forwarding decisions are already made. So we realized that if we want to really do kind of congestion-aware multipathing or advanced flow and congestion control, we really need to make that congestion information available at Ingress pipeline, even before or in the middle of routing and queuing decisions are made. So Tofino 2 provides such a new feature. So egress queue informations are available in Ingress match action unit. And then by doing so, any Ingress packet can have a visibility of many different queues from all 4 different egress pipes. Control plane can actually select a set of egress queues to monitor by this new feature. And then the user can also choose between update triggering modes, whether the queue depth change will be updated from the queuing system back to Ingress pipeline for every change of the queue depth, or maybe you can, if you can deal with a little bit less granularity, but also control the number of queues to monitor, then actually we can also do color-based change in triggering. So number of use cases, yes, congestion-aware multipathing is one thing, and source quenching that we are going to talk more about in the next slides. Before that, I have a simple snippet, a very simplified snippet of this use case to demonstrate how this feature can be represented in P4. So let's assume that we have 1,024 queues monitored by this feature. So we have just a simple register defined, and the values of the registers are updated by a separate thread, which is not shown in this snippet. And we define this ingress control flow, and we have a set of actions to read the queue depth value out of the queue register based on the index. And the index is given by this exact matching table. So here we assume that the egress port and queue for this particular packets are already determined by the queuing system. I'm sorry, the routing table in the ingress pipeline. And then we match on those two fields and get an index and read the queue depths of the queue. So in this apply code block, by executing this table, we make this queue depth information available in this metadata. So you can do many different things, including kind of creating source quenching packet directly back to the sender. So going back to source quenching as a use case, yes, obviously we need to be able to generate a new control packet to convey that information back to sender, some form of congestion information back to the traffic source. For that, there are multiple ways to do that, but Tofino has a packet generator in Ingress, and Tofino 1 supports 3 different triggering conditions, including some periodic timer, or the packet can be generated as a reaction to the link down event, or packet recirculation. But to better support this kind of event-driven packet generation use cases, Tofino 2 allows any ingress packet to trigger a packet from the packet gen engine. So using the P4 level flexibility and match action pipeline and tables, user can write a P4 program that defines any arbitrary event or stateful event or stateless event and trigger the packet gen. So while doing so, the ingress packet and in P4, you can define any arbitrary metadata and provide it to the packet gen engine. And then that information will be prepended to the new packet generated by the packet gen engine, so that the ingress pipeline can make use of this additional metadata for routing or any other stateful process. So yeah, we talked about source quenching as the first use case. You can just imagine that Rocky version 2 DCQCN has a congestion notification packet generated by the receiver, but we can actually offload that logic into the switch and use this packet gen to create such a control packet. Or you can also even do hop by hop flow control, even kind of crafting PFC packet using the P4 driven logic, so that standard PFC packet can be generated using packet gen, and then do some flow control with the neighboring switches. So benefits of doing or generating such control packets using this ingress packet gen engine is in 2 folds. First one is whether this control packet is destined to the immediate next neighbor, or some of the control packets are destined to the multi-hop away n-host nodes. That would be the case for the source quenching. Then we would definitely want this control packet to be looked up by this routing and also multipath table, so that we can do the proper load balancing, etc. And doing so, using this packet gen engine enables us to inject the new control packet directly in the parse of the ingress, so that you can reuse the ingress tables for routing and multipathing. Of course, you can do something like multicasting or mirroring. In that case, those the mirror or multicast copies are injected into the queuing and traffic manager system, but then either you have to duplicate those routing and multipathing tables somehow in the egress or the mirroring engine logic, or recirculate those packets back to Ingress if you want to reuse the Ingress side tables. Then recirculation can actually cause additional kind of delay. And especially for congestion notification use cases, we want to save any save the feedback delay as much as possible. So these are the two benefits we can think about. So this is the kind of ongoing use case demonstration using the P4 snippet. We have two control blocks, ingress and ID parser, ingress deparser. And his queue select is the same table that we defined in the previous slide, which provides the egress side, the queue depths of the particular packet. And here we compare the queue depths against the threshold. If it's larger than threshold, then we just execute this simple action package and pre, which meaning that we form some metadata. For example, here we are providing the source and destination IP address of the original packet so that they can be used to generate the control packet to be routed back to the original source of this data packet. And this action also sets this simple intrinsic deparser metadata, setting that, hey, I want to trigger package from this ingress data packet. And these informations are used by the ingress deparser. And so first we just simply check whether this intrinsic metadata set. If that, then we just prepend provide the information so that the package engine and then the new packet can actually include this prefix header. All right. So far we talked about two interesting building blocks, having the visibility of queue information in Ingress and using the package gen engine to generate some additional control packet or feedback directly from Ingress. Here we are switching our gear a little bit and showing some additional information, control that we can do in Tofino 2. Tofino 1, or just Tofino, you probably know that in Ingress Pipeline, you can select per queue and port per packet using those match action tables. But that in Tofino 2, we extend the flexibility, allowing some more metadata, control metadata for each packet, so that those metadata can be used to control any other queues in the system. And then the queue that we are controlling by this additional metadata isn't necessarily the same queue that the packet is going into or the coming out of the queuing system in case of egress pipeline. So we have all four pipes in the Tofino and PISA architecture. And using this metadata, any ingress packet can control any queues in all four pipes. And if you're talking about egress pipeline, doing this control from egress, then the packet in egress can control any other queues in the same egress pipe. And there are two types of control can be done using this advanced flow control feature. Per queue, the CPU can choose between these two modes. The first mode is then very similar to PFC in a way such that you can just resume or pause the target queue, but now the resume and pause is directly controlled by your P4 program, not necessarily by the PFC frame coming from the neighboring switches. Or even you can basically generate or subtract additional shaper credits, kind of emulating the token bucket in the data plane. Whether the credit is packet credit or BPS credit, it's based on the existing per queue shaper configuration. And this addition or subtraction of the shaper credit coexist with the existing the rate control shaper rate control. So shaper itself has a rate and also burst setting. Based on that, the credits are periodically generated, and we still can honor that scheme. On top of that, P4 program in Ingress or Egress can decide to add additional credit or subtract some more credits out from that existing queue credit pool. So one interesting use case is kind of rotating strict priority. So it has been presented in NSDI 18 and 20 for approximate fair queuing and calendar queuing system. So we all know about the strict priority scheduler that exists in Tofino and many other high-speed ASICs. Strict priority means that you have let's say 8 priority queues, priority 0 as the highest one, and priority 7 as the lowest one. But let's say if the priority 0, the highest priority queue, get empty, then we can actually repurpose the queue as a priority 8, as the lower priority having the lower priority than priority 7. By doing so, you can actually rotate the priority ordering infinitely, and then approximate many different more flexible queuing system like a calendar queue or even something like a PIFO. So this is a very simplified example of executing such an action. So we assume that rotating strict priority scheduler, and to implement that, we should be able to pause a high priority queue once it gets empty. So we also assume the same queue select table from the first slide. And in that case, in this case, we are getting the depth of the queue, but the queue is not necessarily the queue that this particular packet is going into, but any queue that you want to control. So based on the queue depth information, we make sure that the queue is now empty. So then we can just set a number of additional intrinsic metadata that Tofino2 provides. So in this case, the QFC mode 1 means that, hey, we are actually now doing this advanced flow control from data plane. And then the credit field, in this case, carry binary information, 1 for pause and 0 for resume. If the queue is configured to do shaper credit addition and subtraction operation, then in that case, then the credit field is carrying integer value for additional or the credit value that we want to add or subtract. All right, and obviously you can also imagine this credit control or the flow control scheme can be used to create something like a closed loop rate control between egress pipe and then queuing system. Okay, so now we talked about the 3 new building blocks, programmable building blocks available in Tofino2. And there are many different use cases we can think of, but let's first focus on source quenching as a main use case. So what is the problem statement? Existing conventional congestion feedback ECN or RDMA, or using INT for something like a HPCC, the feedbacks are all can be generated by the switch, but they are eventually routed back through receiver. So if there's no congestion happening, the feedback loop is pretty short, and it can be close to the congestion-free minimum RTT, which is tens of microseconds. But let's imagine that there's a high incast just happening right now in this particular queue, and there is a new flow just starting from a new sender. And the first packet of the sender has to wait for the entire queuing delay, which can be large up to 1 or 2 milliseconds, the 2 orders of magnitude larger than minimum RTT, to convey the congestion information to receiver and echoed back through ACK or CMP packet, so that the sender will learn about that ongoing congestion. Then this can actually aggravate ongoing congestion based on which congestion control scheme is used. For example, something like a DCQCN doesn't kind of slow down when there is no act, because it has a kind of policy like no news is good news. So unless there is no congestion notification coming back, DCQCN candor can continue to transmit and attribute to the ongoing congestion. So source quench is, as we briefly discussed in the previous slides, can be a solution. But as we know, where it didn't really take off in the wide area internet. There are multiple reasons, but two major reasons is that, or one major reason is that it's hard to build a trust model between the subsystems or devices in the wide area internet, and also enforce interoperable packet format and also semantics between all different implementations. So this is quite similar to ECN. You know, ECN is just single bit feedback from switch back to sender, but it's not really deployed and used in the wide area internet. But we see that ECN is very widely used in the data center networks because we can have a better trust model. And then we are arguing that we can also apply the same capability to revisit source quenching. And as we have discussed in the previous slide, then the programmable data planes can now give us additional building blocks like congestion information becoming available in Ingress, and also programmable packet generation enables very fast generation of those control packets back to sender. So in a sense, this is the fastest possible feedback that one can get from the ongoing congestion in any kind of reactive congestion control scheme. So then what is exactly source quenching we are talking about? Here I'd like to say that we don't see a source quenching as a particular solution or very well-defined concrete protocol. I would say source quenching or source quench is a generic mechanism to convey many different congestion information in a fastest possible way from congested switch back to sender. So then it's up to each network operator or P4 programmer's decision when to generate the source quench, whether it can be triggered by something like based on queue available in Ingress, or it can be triggered based on tail drop. Then the source quench packet will basically carry the sequence number and it will serve the role as a NAC. Where we can generate, it can be generated from Ingress or Egress and many different subsystems of system, as switching subsystem. But we made a pitch that Ingress is a better place for fast detection and notification. Then what to do with the quench? DCQC and CMP is another way so that the sender can reduce the rate in a same way where it kind of controls the rate upon the reception of CMP, or it can be a NAC to trigger the fast retransmission, or we can also implement a pause as opposed to PFC, which causes head of line blocking in the core switches or fabric switches. We can directly pause the source of the traffic that caused the congestion. And it can also carry additional information like INT for HPCC, or the failure rate computed for RCP, or the number of competing flows. So in any information that sender can make use to do the fast and then accurate rate control. So here, let's talk a little bit more about the pods. Switch can easily compute the time needed to drain the particular queue down to a certain level. We don't want to drain the queue down to 0 because then may create a queue underrun, and then we are not going to utilize the links bandwidth fully utilized. It will be hard to fully utilize. So we want to maintain a small, the minimum queue depth, which is typically the queue depth used for the as a ECN threshold, ECN marking threshold. Then once that kind of draining time is computed, it can be easily handed into the source quench packet, and the source, upon the reception of quench packet, it can just pause its transmission for the specified draining time. While doing so, the queue can still drain the packet already queued up, and those in-flight packets can deliver the congestion information like an ECN and reflected by the receiver back to the traffic sources in a form of ACK or CMPs. So then underlying congestion control can learn about those congestion to some degree and do proper rate or window adjustment. In that way, source pause can actually coexist with underlying congestion control scheme with some minimal interactions. Like I said, the pause time computation should be aware of the ECM marking threshold so that we don't create a queue underrun, but also the pause time can be considered in terms of setting up the retransmission timeout at the NIC side or nHost side transport protocol. Okay, so I think this is the last slide. I think we are ready for Q&A.
All right, cool. I think if you can stop sharing your slide, we can come back to the roundtable session. Yeah,
that's true. Okay. Stop sharing. Okay.
All right, cool. So yeah, great talk, JK. It seems like Tofino 2 has a lot more flexible knobs now to do these interesting scheduling operations compared to Tofino 1. So I think let's begin with a sort of a controversial question, which is like, you talk about source quenching, but the question is like, is the enabler for doing this today in data center is the trust model of the data center itself, or is there anything specific about the technology innovation in the switches that is making it possible today? So in other words, can we not just use fixed function switches with support for source quenching like the one you discussed and just deploy them in the data center?
This is a very interesting question. Yes, the better trust model is a necessary condition so that we can even consider source quenching in data center networks. But efficient realization requires kind of timely access to congestion information and ability to generate such a control packet in time. I'm not aware of a fixed function architecture capable of such a timely detection and handling of such a control packet generation at high speed per packet basis. Mm-hmm. One can actually build such a, I think, fixed function. It is a boilerplate answer. You know, okay. Any feature you are fancy about, you can always build a fixed function logic in a high speed ASIC. But then this wouldn't be able to support, you know, such a recent proliferation of different congestion control scheme. Source quenching, to my definition, like I said, it's a kind of generic scheme that can carry many different informations. But if we say that, hey, source quenching must be just to pausing, or it should be just CMP, like a DCQCN, then we don't have a flexibility to support some other use cases like INT packet directly generated by the switch back to traffic source, so that we can even, I don't know, accelerate HPCC or HPCC++. So yes, having such a flexible building blocks and then present them to different users are basically our motto and goal at Barefoot when we design hardware and software building blocks.
Okay, cool. So it seems like there's enough sort of variation in the kind of congestion control algorithms you want to implement that you want to have sort of a feature-proof and future-proof building blocks in the switch. Cool.
Exactly.
So okay, so coming back to Tofino 2 then, like I think people like audience will be interested in knowing more about what is new in Tofino 2. And then your point about like you made this sort of queue information available in the Ingress pipeline. So the question is like, why was that not available in the first version of Topino? Was there any like architectural implications that you took care of in your like this revised version of Topino? And other than that, what is new, like other than these three building blocks that you talked about? Yeah.
So like in PISA or Tofino architecture, as well as other high-speed packet processing ASIC, the packets are flowing through a set of strict pipeline of ingress stages and queuing subsystem and egress stages. And to be able to support such a guarantee high-speed packet processing, one packet per cycle, usually the safer memory is local to each stage and they are not really shared. That means that information also flows from ingress to egress through the queuing system, making some information from the later stage back to the earlier stage need some recirculation, or basically there is a cost involved. And Tofino was the first chip of this kind, and then we realized that this particular feature that making egress key information available ingress is very critical for lots of congestion or congestion aware mechanisms. So yeah, we paid a price. And then we added a kind of programmable way to also make use of this information. Yeah.
Okay.
Because
cool.
it's important we did it. Yes. And then we were able to do it, and then I'm glad that it's ready out. Yeah.
Cool. So
for your second question, yes. Sorry.
Go ahead.
You asked for the other new features. Yeah. So there are a number of very interesting features, like as simple as min or max operation over the multiple values in the safer memory or metadata, or you can also support 16-bit assigned integer division. And if you look at some more bigger features like hardware learning, but not as a just fixed function hardware learning for one particular exact matching table, we kind of try to push multiple building blocks that can be composed together to implement hardware learning. And those the individual building blocks can be used for something others. So some example is something like a stack data structure between data plane and control plane. So either one of them can actually push and the other can pop.
Okay.
And there are a number of other features, but I think it may deserve a separate session.
Okay. So I think moving on to this point about like new features in Tofino, is it like all of them are exposed as extern in the P4 language, or are there other sort of APIs to them? Like, are there some that are accessible through runtime, or all of them are accessible through P4?
All of them are accessible through P4 to some degree, but there are some configurations will be done by the control plane. For example, for the advanced flow control of any queue in the queuing system, we talked about basically two different modes, right? Just simple X on and X off, pause and resume of the queue, or using the same metadata data structure to add or subtract some additional shaper credits.
Okay.
Which mode you want to use between these two is up to the control plane.
Okay.
But it's kind of similar to existing interaction between P4 and then queuing subsystem. Whether which priority and then what kind of shaper configurations are done for each queue is not really known to P4. It's done by control plane, but it's up to the control plane or programmer's decision to make the coherent configuration and P4 programming based on the kind of queuing policy you choose.
Okay, interesting. So I think the other question about this Tofino 2 architecture, when I was going through your slides, is like you're introducing a lot of other events in the switch. So do you have any idea like how does this differ from the event-driven switching model that was proposed last year in Hotness? Like the idea there is like you want to sort of trigger the pipeline based on events that are non-packets, that are like other than packets. So is there a similarity in this architecture here, or what are the
Oh
differences in
yeah,
your mind? Yeah.
absolutely. As I remember, the paper proposes the multiple logical pipelines or functional
Mm-hmm.
pipelines, one for each type of event,
Mm-hmm.
right? The normal ingress packet event or in-queue or DQ event.
Mm-hmm.
And there are some set of global memory um, that for the global state that share between multiple pipelines.
Mm-hmm.
I think that realizing such a multiple logical pipelines, one for each type of event, um, in also multiple different physical pipelines is possible in, I think, lower speed bandwidth devices, but high rate packet processing engine, it will be challenging because of multiple regions that you may know. So in a sense, in Topino, we are kind of collapsing these multiple logical pipelines into the smaller number of physical pipelines. But like you said, each event is kind of modeled as another packet triggered by different type of events.
Okay.
I think there are multiple also kind of challenges mentioned in the paper about when we do this collapsing, then we need to think about how wide a pipeline can be so that you can handle many different events at the same time. So these are also I think open, interesting, challenging questions, and we can, as a community, we can look at together.
Okay, awesome. So in summary, it seems like in Tofino 2, you can trigger the pipeline based on certain events, but that event actually translates into a packet that flows through the pipeline.
Yeah,
Is
I
that
mean,
yeah.
Yes, right.
Okay.
Speaking of a little bit of details, I think there is a little bit of delay between different events. For example, Ingress or Egress pipeline detects a certain event based on, let's say, queue depth or other routing change events, and then it triggers a package and engine. So first, the packet needs to hit the deparser to basically. I'm sorry, the egress doesn't have a package end, but it's ingress side. So there is a little bit of delay, pipeline delay, to make that kind of event to be aware. I mean, signal back to the package end and then creating a next packet. So I think if you want something like a back-to-back handling of the triggering event and then event handling packet, then that seems not possible in this particular architecture, and then we may think about a better way to do that.
Okay, cool. So I think so the main topic of the talk was about actually doing congestion control inside switches, which is amazing. Like it seems like it's on the same theme of like offloading sort of functionalities down into the switches. So do you think when you're moving this congestion control and flow control mechanism inside the switches, what is the impact on the high level transport that is happening between the two applications, like a client and a server? Like do you have any idea or sense of like, is there going to be an effect on the overall implementation of the transport when you're doing this thing inside the switches?
Well, so in the last slide, I try to show one case where source quenching can be used as a simple pause, which is a kind of direct replacement of PFC. PFC is a hop by hop pause, having lots of side effects. By just pausing the particular source of that congestion traffic, we can effectively avoid many of packet drops and buffer overrun without having such a PFC side effects. In that sense, it doesn't really change any kind of end-to-end congestion control logic. You can coexist of the existing congestion control schemes, but it doesn't necessarily preclude the possibility of, as you alluded, the possibility of creating a new sort of transport or congestion control scheme that may maximally utilize the benefit of this in-switch notification generation. I think there are a number of work that trying to use switch as a kind of centralized scheduler. So number of transmission demands are kind of collected, known by the switch, and then switch can make a semi-optimal scheduling decision. In some sense, network switches are the prime location, like a real estate analogy, because it is the place where all the communication demands are collapsed and then known. So that's another interesting, I think, direction. Another way to think about is that the server side or the end host side, this congestion control implementation sometimes can trigger lots of control packets. And as far as I know, the PPS overhead or the PPS processing bandwidth is becoming challenging on the end host or also maybe even NIC side packet processing. So if there is a way to offload some of the logic to switch so that it can generate a number of necessary control packets, then we can actually minimize the packet generation overhead from the at the NIC side.
Interesting. That's a very interesting.
That's another way to
think about it. Yeah. Okay, so I think in the end, so right now, and also in the end of your talk, you briefly mentioned about like NICs, like network interface cards. Do you see like these programmable NICs can also help extend this model or scale this model in a certain way alongside working with the switches?
Sure, absolutely. In some sense, like the NIC is the best place to implement end-to-end congestion control scheme, and that's the direction I think we are seeing, right? Currently, they are in software and kernel TCP/IP stack, but they are slightly one by one offloaded down to hardware. And in case of RDMA, everything is offloaded to hardware now. Most of them. But because NIC and host is the best place to get to know and then make use of the application side demand and knowledges. At the same time, the switches can provide the best possible and very rich and fast congestion information back to centers. So I think HPCC is very interesting case demonstrating this kind of nice job division between smart NIC and then switches. Switches providing the rich information, and NICs are making use of the information to do better congestion control and then transport. I think that's the right decision, direction, and I'd like to see more of such a co-design between NIC and switch.
Okay, cool. Okay, cool. So this is a really interesting talk. Thank you for sharing this new sort of features inside of Eno2 and one of the representative use cases. So I think with that, let us thank our speaker for such a great discussion. I hope everyone enjoyed it. Thank you all for listening. And with that, we conclude our session. Stay safe, everyone. Bye.
Stay safe. Thank you. Bye.